Hi everyone, it's Japoo, and today we're going to be talking about related rates. So just a reminder, if you would like to follow along to this video, the worksheet that I'm about to do and the answer key are linked in the description below, as always. So related rates is not the biggest AP topic, but you still are going to see it on the AP test. It may just be one or two questions, but it's still good to understand the concept of related rates so you can get those questions right. Related rates are basically derivative problems, but in real world situations. So derivative word problems, basically. I actually enjoy related rates because I like to do word problems, and this is one of the instances on the AP test where you will be probably given a word problem to solve. Alright, so let's get to it. First, I'm going to talk about the steps that you should take when approaching a related rates problem and then how to solve it. So the first step that you should do is locate the function. Now, you could be given the function in the problem, as we're going to see in some of our examples, but sometimes you're also going to have to find the function, either geometrically, so the function might be the area of something, and you have to know like the area formula, and that area formula will be your function. Sometimes you have SOHCAHTOA formulas that you have to use. We have examples of both of those instances in this worksheet. If you have to find the area of anything harder than this, or if you have to find, if your function is going to be anything harder than this, they're going to give it to you. So like 3D shapes, on the AP exam, they will give you the formula, so you don't have to worry about that. After you locate the function, you're going to take the derivative of both sides, implicit differentiation, So basically, that means that every variable in your function has to have a prime or derivative, because instead of like x being the variable that can just kind of disappear, when you take the derivative, you actually are taking all of the derivatives with respect to t. So this will make a lot more sense when we start the problems, but just know that every single variable in your function, when you take the derivative of that function, you have to include the derivative when you're taking the derivative. It'll make more sense when we start the problems. Number 3, what you have to do is plug in variables. This seems pretty straightforward, but make sure that you're plugging in the right things for the right variables. So for example, if you see a rate, like if a rate is given to you, that's a derivative. And if it's just a regular like number, and it's not a rate, then that'll just be like your variable. So make sure that you know the difference between those two, because sometimes it's easy to switch them up. And then just a few things to keep in mind while we're doing these problems. If you have one less unknown, you use the original function to find that unknown. So if it's not a given value, you basically will have to use the original function that we located in step 1 to give you the value for that function, or for that variable that you don't know. And then the other thing to keep in mind is that if the quantity is decreasing, then the derivative is negative. So if you have a rate that's like, if something is like maybe slowing down, that means that that rate is going to be negative. So make sure that you pay attention to the wording in the problem, because that'll give you a clue about whether something is positive or negative. So for example, if in the problem the variable is not changing over time or something, then that means that the rate is equal to 0 for that variable. If that variable is like getting smaller over time or something like that, like if the problem tells you hints that the variable is getting smaller or decreasing or anything like that, then your rate is going to be negative. Again, this will all make sense, hopefully, when we start the problems, but just keep these things in the back of your mind while we're doing it. Okay, so number one is actually very straightforward. It's not really like a word problem, but it kind of shows you, like there's no like real life situation or anything, but it kind of shows you the steps that we have to take when approaching related rates problems. So the first thing that we're going to do, right, is locate the function. In this case, the function is actually given to us. The function here is z squared equals x times y, right? So I'm just going to go ahead and circle that. And then after we find the function, we have to take the derivative of both sides, right? So keep in mind that here we have a product rule, and then also keep in mind that every single variable needs a derivative. So on the left side of our equation, we're going to take the derivative of z squared, which is 2z, times dz over dt. Okay, you can see how I'm including the derivative of the variable in its like general derivative, I guess. And then on the other side, we're going to have dx over dt times y plus dy over dt times x. This is because we're including the derivative of every single variable. So if we weren't, technically the product rule would be take the derivative of x, multiply it by y, and then take the derivative of y and multiply it by x. So if we weren't marking down the derivative of every single variable, we would have y plus x as the derivative. But since we are, the derivative of x we write down as dx over dt times y stays the same, plus the derivative of y, dy over dt times x stays the same. So I hope this helps kind of demonstrate step 2, where we have to like keep the derivatives for every single variable. Make sure that you notice that even x, you have to keep the derivative for. Like you have to write that down. Okay, so now that we've done that, we're going to keep going to step number 3. So what we're trying to find in this case is dz over dt, right? Like that's what the question is asking. So I'm going to go ahead and circle that. And now we just have to plug in. So we're going to have 2 times dz over dt, because we don't know that quantity, plus 5 times, and then we're not actually given a quantity for y in the problem, so we're going to have to figure that one out. So I'm going to leave a space for now, plus 3 times 4, and both of those are given. To figure out the quantity of y, we're actually going to just go ahead and use our original equation, z squared equals x times y, and plug in 2 for z. 2 squared equals 4y, because x equals 4. And we're going to get y equals 1. So here we use the original equation to find a variable that was not given. And then we're going to plug that back in to the derivative equation that we have. And our answer will be 17 over 4, because we're going to get 5 plus 12, and then we're going to divide by 4 to isolate dz over dt, which will give us 17 over 4. All right, so that's it for the first problem. As you can see, the steps are pretty clear once you understand what they mean, and you can approach all related rates problems exactly like this. So for our next one, we are going to follow the same kind of steps. We're first going to locate our function, which here is y equals x squared minus 5. We're given that function. And then we're going to take the derivative. So we're going to get dy over dt on the left side is equal to 2x times dx over dt. Remember that the x's need derivatives still. Minus 5 times dx over dt. And so luckily in this problem, we're actually given every single variable that we need to find dy over dt. So we don't actually have to use the original function for everything, and we can just go ahead and plug in everything. So we're going to get dy over dt equals 2 times 2 times negative 1 minus 5 times negative 1 equals 1. And that's our answer for this problem. So these first two problems were kind of easy, especially since we were given the function. But now in this one, you'll see that we're actually not given the function, and we're going to have to locate it ourselves. But as you can see, the question is asking what rate is the area of the square increasing. So we know that we're dealing with the area of the square, right? And we know the formula for area of the square. But really fast, we're just going to draw out a square, just so we can kind of get our bearings. And we know, I'm going to label one of the sides as S. So we know that squares all have, like all the sides in a square are the same. So the area of a square is A equals S squared, right? So that's actually going to be our function, since we're dealing with an area of a square here. So A equals X squared is our function. Once we've located that function, we can continue on to our next step, taking the derivative of both sides. So when we do that, we're going to get dA over dt equals 2s times ds over dt. And then we're going to plug in. So what we're looking for in this problem is the rate the area of the square is increasing. So we're looking for dA over dt, right? And then we are given the rate that the side is increasing. So we're given ds over dt, and notice how I said the rate, the side is increasing, not decreasing. So since the rate of the side is it's increasing at a rate of something, that means that the rate of the side is positive. So ds dt is actually going to equal a positive 7. And then unfortunately we are not given the value of s in this problem, so we're going to have to find that using the original equation. Let me just go ahead and write that down. So 7 again for the rate. And now we're going to use the original equation. We're going to use a equals s squared to find s. So in the problem, it tells us that the area of the square is 16 centimeters. So basically s squared is going to equal 16, so s will equal 4. And then we can go ahead and plug that into our derivative equation and then solve for dA over dt. And the answer is 56. So again, not too difficult if you know what you're doing. So if you remember the steps to approach and solve related rates problems, they shouldn't be too difficult. So now we're dealing with the area of a rectangle, right? The question is asking how fast is the area of the rectangle increasing? We are not given the function in this problem, but we do know what the area of a rectangle formula is, so we can figure that out ourselves. So I'm just going to go ahead and draw a rectangle, and I'm going to label one side the width and one side the length, W and L, since all four sides of a rectangle are not equal, like a square. And the area of a rectangle is basically L times W, right? So our formula for in this case is going to be A equals L times W. Very straightforward. So that's our function. We've located our function, and now we're going to take the derivative of both sides. Watch out for the product rule in this case, and make sure that you take that into account when you're taking the derivative. And what you're going to get is dA over dt equals dL over dt times W plus dW over dt times L. This is kind of similar to the first problem that we did. So make sure that you put the correct derivatives in the correct places. Like, don't mix dW and dL up, because that'll give you a different answer. So now that we have our derivative, we are going to start plugging in. All right, so I believe that we are actually given everything in this problem right. So we don't actually have to use the original equation to find anything, which is good for us. So basically we're going to get 2 times 5 plus 4 times 3 equals 22. And 22 is our answer. I just wanted to point out again that in this case, the length of the rectangle is increasing at a rate of 2 centimeters per second, and the width is increasing at a rate of 3 centimeters per second. Since the word increasing is related to both of those rates, we know that both of those rates are going to be positive, and therefore both dL over dt and dW over dt are going to be positive. All right, so continuing on, number 5. So number 5 is a little bit trickier. It's not as straightforward as the other ones. So in this case, we're dealing with a ladder sliding down a wall. So let's just draw a picture of what we think this ladder sliding down a wall looks like, and then maybe we can find a formula that'll work in our case. Basically, that's kind of what the ladder sliding down a wall looks like, right? The y-axis is going to be the wall, right? The x-axis is the ground. And that diagonal line is the ladder. So basically, a ladder sliding down a wall makes a triangle. And what we can do in this case is actually use the Pythagorean Theorem to find our solution. What we're trying to find right now is the rate at which the bottom of the ladder is sliding away from the wall. Okay? So our formula that we're going to use is x squared plus y squared equals z squared. That's the Pythagorean Theorem. And so it's always good, I think, to draw a picture when you have these kinds of problems to help you figure out what variable is associated with what. But as you can see right now, we're going to call the wall y, the ground x, and the ladder z. Okay, so now we're just going to take the derivative of the Pythagorean Theorem formula. And we're going to get 2x times dx over dt plus 2y times dy over dt is equal to 2z over times dz over dt. Okay, and now that we have that, we're just going to start plugging in. So what we're going to do is basically start off with 2 times 12, which is x, we're given that in the problem, times dx over dt. We are not given that in the problem. That's actually what we're trying to find, I believe. Plus 2 times, and we don't know what y is, times -3 equals 2 times 13 times 0. So let's go over this equation again, or our plugins. So we get 2 times 12, since the bottom of the ladder is 12 meters away from the wall. So the x value, the distance of x, is going to be 12, times dx over dt, which is what we're trying to find. We're trying to find the rate at which the bottom of the ladder is sliding away from the wall. So we're trying to find the rate of x increasing. So that's dx over dt, plus 2 times, and we don't know what y is, so we're going to have to find that, times -3. Watch this negative. Watch out for that. In the problem, it says that the top of the ladder is sliding down the wall. The ladder sliding down means that the distance of y is getting smaller. So the rate in this case of y is negative, and that's how we get a -3. And then that's equal to 2 times 13, and we're given the fact that the ladder is 13 meters long in the problem, times 0. The rate of the ladder in this case is 0 because the length of the ladder is not changing. The length of the ladder is not increasing or decreasing, so the rate is 0. And we know that because it's a ladder. Like, it's not going to change. It doesn't tell us in the problem that it changes. It just tells us in the problem that the ladder is sliding down the wall. So now that we have this, we're going to find what the y value is in this case. And to do that, we can use the Pythagorean theorem. But also, if we recognize that the ladder sliding down the wall forms a right triangle, and if we've memorized our right triangle, our usual right triangle formulas, there's such a thing as a 5, 12, 13 triangle, where if two sides are 5 and 12, or two sides are 5 and 13, the third side is going to be the third value. So in this case, we have x is equal to 12 and and z is equal to 13. So y has to be equal to 5 because it is a 5, 12, 13 triangle. If you don't want to memorize these typical side lengths, then you can always just use the Pythagorean theorem. And for our answer, we're going to get 5 over 4. So the rate at which the bottom of the ladder is sliding away from the wall is 5 over 4 meters per second. Now we have number 6. So again, we're going to draw a picture like we did in the last problem. And in this problem, a rocket is being launched vertically from a launch pad, and somebody's watching that rocket being launched. So this is going to be a triangle. I'm just going to go ahead and give you that heads up. And it's going to be a triangle because somebody is looking up at a rocket, and that's a diagonal line since the rocket was launched horizontally away from the person. So Gertrude, or Gertitude, is that a name? Gertitude? Gertitude is watching this rocket being launched up. So the rocket is being launched vertically. So the path of the rocket is going to be the y value. And in this case, we're looking for the rocket's velocity when the angle is pi over 3. So we're looking for the rate of y. Now, Gertrude or Gertitude or whatever the person, whoever she is looking at the rocket at an angle of pi over 3. So she's looking up at the rocket. So she's going to be at the angle where I drew her right here, because she's looking up at the rocket, and this is the launch pad right here. So in this case, we're not actually going to use the Pythagorean theorem, even though we do have a triangle. We're actually going to use SOHCAHTOA rules because we're dealing with an angle. We're going to use tangent, the formula for tangent, because of the sides that were given. Tangent is equal, the tangent of an angle is equal to opposite over adjacent. And we're looking for the derivative of y, right? We're looking for the rate of y. So we have opposite, and we're given the horizontal distance between girtitude and the launch pad, which is an x value, which is the horizontal value right here. So that's adjacent. So our original function that we're going to locate, that we just located, I guess, is tangent of theta equals y over 10. Very straightforward, if you know your SOHCAHTOA rules. And now we're going to take the derivative of both sides. So the derivative of tangent theta is secant squared theta times derivative of, or d theta over dt. That's the derivative of theta. And that's going to be equal to 1/10 times dy over dt. I did not do the quotient rule for y over 10. I just took out a 1/10 and then took the derivative of y. Now this problem looks a little bit tricky because we do have secant squared of theta, and we're going to have to plug in pi over 3 for theta. So off to the side, I'm going to solve secant squared of pi over 3. So secant squared of pi over 3 can also be written as secant pi over 3 squared. This is the same thing. This means the same thing. Secant is equal to 1 over cosine. So we can manipulate this equation so that we get 1 over cosine pi over 3 and all of that squared. Cosine of pi over 3, according to our unit circle, is 1/2. So what we're going to get is 1 over 1/2 squared, all of that in parentheses. 1 over 1/2 is going to equal 2 because we're going to divide 1 by 1/2 and we multiply by the reciprocal, so we're going to get 2. 2 squared is equal to 4. So secant squared pi over 3 is equal to 4. So this term right here is going to be equal to 4. Another thing to note is that the derivative of theta, d theta over dt, is equal to 0.4 radians per minute, right? In this problem, I'm actually going to write 0.4 as 4 over 10, just because it's easier in this case to deal with fractions than it is to deal with decimals. But you can write it either way you want. But just know that 0.4 and 4 over 10 is the same thing. So now that we're plugging in, we're going to get 4 for secant squared of pi over 3, since theta equals pi over 3, times 4 over 10, that's the rate that theta is changing, equals 1/10 dy over dt. And if we solve for dy over dt, we're going to get 16. So the rocket's velocity when the angle is pi over 3 is going to be 16 kilometers per minute. Okay, so that's our answer. And we're going to move on to the next problem. Number 7. This is a plane flying over an airport. So again, this is going to be a triangle, and I will tell you why. So what we're going to have is, it's going to be a right triangle too. And this is because the airport is going to be on the ground, right? So that's this rectangle right here. That's the airport. The plane has just flown directly over the airport and is now 5 miles away from the airport. So the z is 5 miles away, right? And so we want to find how z is increasing. We want to find the rate of z. So the reason why it's a triangle is because the plane is not directly over the airport at the point that we're trying to find. The plane is 5 miles away from the airport, and so we have a triangle. Okay, so this means that we're going to do the Pythagorean theorem because we're trying to find the rate of z, and we have all the side values. So this is going to be the same derivative from number 5, 2x times dx over dt plus 2y times dy over dt equals 2z times dz over dt. That's the derivative. So now we're going to plug in. And we have some values in the given in the problem. But one thing that I wanted to point out that was not given in the problem is dy over dt. dy over dt is equal to 0 because the altitude is not changing. The planes in general fly horizontally for the most part unless they're taking off or landing. In this case, the plane is neither taking off or landing, and it says in the problem that the plane is flying horizontally. So that means that this altitude of 2 miles remains constant throughout the plane's flight. So y is not changing. The plane is not going up or down, it's just going horizontal, right? So the rate of y, dy over dt, is equal to 0. Now we can plug in. We're going to have 2 times x. We don't know what the x value is, so we're going to have to find that using the Pythagorean theorem, which is our original function, times 500. We're given that in the problem, plus 2 times 2, that's the altitude, times 0, because as we said, the altitude isn't changing, times 2 times 5. 5 is the distance the plane is from the airport, times dz over dt, which is what we want to find. So now we're going to use the Pythagorean theorem to find x. We're going to have x squared plus y squared equals z squared. And if we plug in 5 for z and 2 for y, x is going to equal square root of 21. So now we're just going to go ahead and plug that in to our derivative equation. And then we're going to solve for dz over dt. And that gives us 100 square root 21. If you want, you can plug that in your calculator and get a number without a square root, but I just left it as is because we can't simplify square root of 21 any further. All right, number 8 involves 2 cars moving away from the same point. So this is also going to be a triangle, and I will tell you why in a minute. We have car A moving west, moving left, moving west from point C, and car B moving south from point C. So I'm going to say that point C is our intersection. It's the starting point. It's where both of the cars start moving because the problem says that 2 cars start moving from the same point. So I'm going to say that C is that same point. C is the intersection that they both start moving from. So we find that 1 car travels west at 40 miles per hour. I'm going to call that car A, and I'm going to say that since it's moving west, this is where car A is going to end up at 2 hours or whatever. We also have another car moving south at 30 miles per hour. I'm going to say that that is car B, and car B is going to end up over here at 2 hours later. So that's how we get this triangle. Now we're trying to find the rate. We're trying to find at what rate the distance between the cars increase 2 hours later. So we're trying to find the rate of this, and I'm going to label that z. So we're trying to find the rate of z. So, you guessed it, we're going to use the Pythagorean theorem. X squared plus y squared equals z squared. You're going to probably see a lot of the Pythagorean theorem in related rates, but just remember to draw the picture just in case it happens to not be a triangle and they're trying to trick you or something. So we're going to take the derivative. We're going to get 2x times dx over dt plus 2y times dy over dt equals 2z times dz over dt, the same derivative that we found in number 7 and number 5. And now we're going to plug in. This problem is a little bit tricky because it does not give you the values for x, y, or z. And so we can't actually use the Pythagorean theorem at first because we have to find at least 2 of these values, right? We have to find at least 2 variables, maybe x or y, x and y, to then find z via the Pythagorean theorem. What we want to do in this case is actually recognize that we're trying to find the rate 2 hours later from the starting point. And the cars start moving from the same point at the same time. So we're actually going to use the distance formula, d equals rt, or dirt if you will, to find the values of x and y 2 hours later. So after 2 hours, let's start with x. And let's start with car A, I guess, x, which is the x value. X is equal to the distance that car A has traveled after 2 hours, right? So we're going to plug in the numbers that we have to find the distance in our distance equals rate times time formula, dirt. So we're going to have rate equal to 40 times 2 gives us 80 miles as the distance. So x after 2 hours is going to be equal to 80. Let me move myself over here so we can see. Y after 2 hours is going to be 2 times 30, because our rate is 30 for y, equaling 60 miles. So after 2 hours, y equals 60 miles. Then we can find z using the Pythagorean theorem. And if you recognize that this triangle is actually a multiple of the 3, 4, 5 triangle, you'll know that z is equal to 100 because technically this is a 3, 4, 5 triangle, but all of the sides are multiplied by 20. So 3 times 20 is equal to 60, 4 times 20 is equal to 80, and 5 times 20 is equal to 100. But anyway, you can also use the Pythagorean theorem to find z if you want. But for the other 2 variables, you do have to use a different formula. After we get these variables, we can finally plug in to our derivative equation to solve for dz over dt. So what we're going to get is 2 times 80 times 4 times 40 times 2 times 60 times 30 is equal to 2 times 100 times dz over dt. So these 2 here are our rates, and then these are our x and y values. So dz over dt is equal to 50. So this problem was a little bit more tricky, just because we did have to use a formula different from the original function that we located to find some unknown variables. But if you kind of think about it logically, it does make sense. So let's take car A, for example. Car A travels 40 miles per hour. So, and we have a total of 2 hours, right? The car's travel has been moving along the horizontal axis in the west direction, I guess, for 2 hours. So what does that mean? That means that the car has traveled 40 miles in 1 hour and an additional 40 miles in the second hour, which gives us 80 miles total. So if you kind of think about it logically, it does make sense, and you don't actually have to know the distance formula, even though the distance formula, it's exactly what I just said, but you can like rationalize it and logic it out. So be careful for those kinds of problems because they will try and trick you and it might seem a little confusing, but if you think about it and read the entire problem and look at all of the values that you have, you will figure it out. If this video was at all helpful to you, please give it a like and subscribe to our channel because we have a lot more calculus videos, probably covering like every single topic that you can imagine and more. So check those out. Thanks so much.